Okay, so next week we have the midterm exam. Okay, we'll start at 7 o'clock. And you know, I've scheduled an hour and a half, maybe a little bit longer, maybe an hour and 45. We'll do that. Okay, so we'll say about 1 hour 45 minutes for the test. Or I should just say 1 hour, not about. We'll do 1 hour 45. Because I think on the test it says 90 minutes, but I'll extend it. It's all multiple choice. And I've listed off a few topics on the website that I think are relevant to study, but pretty much it covers up through chapter 6. Okay, so basically chapters 1 through 6. And so you need to bring what do you need to bring? Pen and pencil, or pencil, pen, your reference tables, calculator, and a photo ID. Okay, I guess just in case someone's trying to take a class for someone else. I don't know, but I'm supposed to check at least once during the quarter. Okay, and I will provide Scantrons, so you don't have to worry about that. Okay, so I will provide the Scantron Forms. Or the bubble forms, they're not. I guess Scantron is a brand name, so they're not officially Scantron, but I'll provide those. Okay. Oh, and you are allowed a note sheet. 8.5 by 11, but one-sided. Okay, and it can be typed, handwritten, whatever you want. Okay, typed or handwritten. Okay, and just make sure you need to make it yourself. I don't think it's going to be an issue here, but sometimes students will make photocopies for each other, and I want every student to make his or her own note sheet. Okay, any questions? Yes?
So there are going to be the quiz questions, or there can be some where it's like multiple choice, like finding something sort of?
So everything is multiple choice there. I do have a couple of questions that are like I don't know, definition / conceptual type things, but it's multiple choice, so you just pick the answer that seems the best or is the best. Yeah. Okay, and then we will have lecture after the exam, so there will be and so that will go from 9 to 10 p.m. So Richard, I imagine you're not going to take the test. So if you want to come to lecture, you don't have to. It'll be from 9 to 10. So
from 9 to 10?
9 to 10.
Oh, definitely.
Okay. All right. So next week, 9 to 10 There will be lecture. Yes. Approximately 35 to 40, something around there. Okay. What's that?
That's awesome.
Well,
so no curve.
So yeah. Okay, so and that's that. Okay, and so today I'm going to cover the rest of chapter 6. We'll do confidence intervals for for 2 samples and the difference between population means, and then we'll spend a little bit of time reviewing, just kind of doing a brief review of the other stuff we've covered. Yes. Yes, what you learned today will be on the midterm, and so today will be some new stuff and then some review. Okay? Let me just think if there's anything else I need to say. I think that's it. Oh, so it's multiple choice, and I have I use the computer to grade. So if you want, I can grade your exam immediately, and you can find out how you did. Or you can wait till you get home, and it will, probably by the next day, it'll be posted on Canvas. So, okay. All right. So let's we'll get into the rest of this. Okay, so let's let's do a quick recap. Quick review of confidence intervals. Okay, so we covered confidence intervals last week, or introduced ourselves, and I said this was our first exposure to statistical inference. Okay, and so what are we trying to do with a confidence interval? What is the point?
With the population being using the sample.
Yes. So we want to. Sorry, let me do this thing again. We want to make a statement about the value of the population mean. Okay. Population mean mu. Okay. But the only data that we have comes from a sample. Okay. And it's important for the math that the sample is randomly selected. Okay. From a sample, randomly selected. If the sample has not been randomly selected, everything that we do with confidence intervals does not apply. Okay.
Is that not just confidence, doesn't it go in the very beginning?
Yeah, for pretty much all of our statistical inference methods assume random selection. Okay. And again, pulling this off is actually kind of difficult, but we're assuming that we've done it. Whoops. Something happened. Okay. Is there like a gesture that? I don't know. Okay. So the only data comes from a sample which has been randomly selected, and so we use the sample mean as kind of a starting point, and then we give ourselves a margin of error, and we end up saying we're this confident that the population mean is between here and here, based on what we see in the sample. Okay, so we use the sample mean as a starting point. Okay, and based on the we find the margin of error. And we say something. We say we are blank % confident that mu is between blank and blank. Okay. So by observing a sample and knowing that the sample has been randomly selected, we can then make inferences about the mean of the population. Okay, and so at the center of the interval we put y bar, and then our margin of error, the plus or minus part, is the combination of a critical value and the standard error, which is S over the square root of n. And we use the t-distribution because we don't know the population standard deviation sigma, so S is a stand-in, and so the t-distribution gives us a little extra breathing room, or it accounts for the uncertainty in S. Okay, and so this creating a confidence interval based on one sample, we can kind of get a range of plausible values of the population mean. Okay. So what we're going to do today is we're going to look at two samples. We're going to take a look at two samples. And so sample 1 is randomly selected from population 1. Okay, and sample 2 is randomly selected from population 2. And the question we want to know, okay, in our question, is the mean of population 1 different from the mean of population 2? So mean of population 1 we will write as mu1. Is the mean of population 1 different Okay, or symbolically we can write and that's what we want to know. So a quote-unquote naive approach would be to take sample 1, make a confidence interval for mu1, and take sample 2 and make a confidence interval for mu2. Okay? And then okay, and then we see, is there any overlap between mu1 and mu2? Okay, so for example, let's say sample 1 has mean 10 and standard deviation something else, and sample 2 has mean 15, okay, and standard deviation something else, okay. So maybe the confidence interval for mu1 is 10 plus or minus 3, which gives us 7 to 13. Okay? And then maybe the confidence interval for mu2 is 15 plus or minus 3, which then goes from 12 to 18, or something like that. Okay? So with this naive approach, we would say, oh, you know, there's some overlap between our confidence intervals, so maybe we're not ready to say that mu1 and mu2 are different. Or I don't know. Does that seem reasonable or something? Or do we have any feelings about this approach?
So you would say that they don't have overlap, even though it's like 13 and 12, they kind of have.
No. So we say there is overlap.
Oh, we do, okay.
So I'm saying this is a naive approach, and we're saying, oh, so there's some overlap, right? 7 to 13, and then over here it goes 12 to 18. So it's possible that mu1 is 12 and a half, and mu2 is 12 and a half, or something like that, right? Okay, and you know, this is the naive approach, and it turns out that if you do things this way, this is like a very almost overly cautious method where mu1, and I would say if this is the data, mu1 and mu2 are almost certainly going to be different. If sample 1 has a mean of 10 and sample 2 has a mean of 15, mu1 and mu2 are almost certainly going to be different. But because we're taking this overly cautious approach, you get a little bit of overlap a lot of times, and if you just say if there's any overlap, I'm not ready to say they're different, then you're gonna end up making these. You're not going to conclude that they're different as often as you should be. Does that make sense? Okay, so this approach ends up being a little bit overly cautious. Okay, so this approach is too cautious. Because the only way for mu1 and mu2 to actually be the same in this situation would be that for sample 1, we happen to get a mu1. Mu1 needs to be high, and our sample happened to be unusually low, or not unusually low, but on the low side. And for sample 2, the opposite needs to have happened. Okay, and the probability of those two things happening together is actually much lower than just getting some random difference or something. Okay, so the approach we want to take is we want to model the difference between mu1 and mu2. Okay, so what we should do is we're going to make a confidence interval for the quantity mu1 minus mu2. Okay, and so this is this is the difference between the means of mu1 and mu2. Okay, so if the two populations have the same mean, then whenever we take two samples, we would expect the sample means y bar 1 minus y bar 2 to be what? Yeah, to be 0 or at least very close to 0. Or close to 0. Okay? And on the other hand, if the two populations have different means, we would expect this to reflect that. But it greatly depends on how big of a difference mu1 and mu2 actually are, right? Okay. So we want to model this thing, and it turns out that we can. We just have to figure out what the standard deviation is of this quantity. Okay, and so well, we need to. Yes, I'm going to write. We need to figure out the standard deviation of the sampling distribution of y bar 1 minus y bar 2. So if we repeatedly took two samples and calculated the sample means and took the difference, and we did this over and over and over and built a sampling distribution, we want to figure out the standard deviation of this. Or this is also called the standard error of, or I should just write standard error y bar 1 minus y bar 2. Okay, and so when if you're trying to find the standard deviation of kind of this of something where you're combining two things, you don't just add the standard deviations together. You have to add the variances together. Okay, and so let's just take a step back. So what we need to do, so just a reminder, standard error of y bar 1 would be what? S over, it would be S1 over the square root of N1 to distinguish between the standard error of y bar 1 and y bar 2. S2 over the square root of N2. Okay. And we want to combine these, but we have to combine not the standard deviations, but the variances. Okay? So to combine, we combine variances, not standard deviations. So what we do is I'm going to square both of these. So I'll have S1 squared over the square root of N1. So this is going to be the standard error squared. It's going to be S1 squared over square root of N1 squared, which just becomes N1. And then I'm going to square this thing, and I get S2 squared over N2. Does that look okay? So all I'm doing is I'm squaring each of these things, and I'm adding them together, because we're combining variances and not standard deviations. Okay, and then so then if I just want the standard error, I just take the square root of everything. And we get the square root of and that's it. Okay, is this okay?
Why isn't the ends, aren't those the square roots, right? Just using, because you're using the same number for both?
I'm sorry? So the N1 and N2 are different, but when I square this, so let me just, so if I were to square this, I would get S1 squared, and then root N1 becomes,
oh, yeah.
So, and I'm just doing that to both of them, and I'm doing that. Okay. Okay, so this is my standard error of y bar 1 minus y bar 2. Okay, and so using kind of the same form for the confidence interval, we're going to get this. Okay, so the confidence interval for quantity mu1 minus mu2, okay? What do you think should go right in the middle? What is our starting point to estimate this quantity? So okay, so let me just a reminder. So confidence interval for mu, in the starting point we've just put the sample mean, and we go plus or minus the margin of error, and we did t star times the standard error, which was s over the square root of n, right? This is standard error. And over here this is the critical value. And right here, this is kind of our estimate of mu. Okay, so that we're going to parallel this or actually all confidence intervals kind of parallel this idea. So what do you think goes right in the middle? What would be our estimate of this quantity based on our samples?
Y bar 1 minus Y bar 2.
Y bar 1 minus Y bar 2, exactly. Okay, so this goes right in the middle. Okay, and then I'm going to go plus or minus my margin of error. Okay, and so we're still going to have to figure out a critical value t star, and I'll explain this part in a bit. But I'm going to multiply my critical value by what?
It's a fancy one. We just
Yeah, the fancy standard error, right? The standard error, which is the combination of the two other standard errors. Okay, and that's it. This is a confidence interval for this quantity. Okay, but now I have to talk about choosing our t star. Okay, so there's our the truth is the degrees of freedom associated with t star when you are combining two different standard errors, it gets really convoluted. Okay, so the actual degrees of freedom for t star is a bit ugly. Okay, and so a lot of times we just use approximations. The computer will figure out the true appropriate t star to use, the true values that we should use. But when doing it by hand, we're just going to use an approximation. Okay. Okay. So when choosing t star by hand, we approximate the degrees of freedom. Okay, and so there's a couple schools of thought. There's kind of the cautious approach, and then there's the one that's a little bit more whatever the opposite of cautious would be. And so, I mean, you're not going to get in too much trouble in either way. Okay, so the cautious would be degrees of freedom is equal to n minus 1 using the smaller of n1 and n2. Okay, and then the other approach, which is the one I like to use in this class, is just add the liberal approach, yeah. Would be n1 plus n2 minus 2. So you're basically just adding the degrees of freedom of sample 1 and sample 2. And the true degrees of freedom is going to be somewhere in between here. Okay. So I think in our class we'll use the liberal approach, I guess, for our class. And that means if you don't find the exact degrees of freedom in the table, always round down. Okay? You don't round up. So Okay, so let's do a quick example here. I'll let you guys copy all of this down. Okay, so this is a silly example because we already know the answer, but we'll try it. Okay, so the question is the average height of an adult male different from the average height of an adult female? Okay, so we already know the answer to this is yes, but we'll pretend we took some data and we're going to try to answer this using a confidence interval. Okay, so here's our data. Okay, sample 1, we will say is men, and sample 2 will be women. Okay, so both samples will have a sample size, we'll have a sample mean, and a sample standard deviation. So let's say we surveyed, randomly sampled 20 men. The average height of these men was 69.5 with a standard deviation of 3.1. And for the women, let's say we surveyed 15 women. The average height was 5'4". We'll say 5'4.5". 64.5 with a standard deviation of 2.8. I'm just making these up. Okay? Alright, so go ahead and make, so we will say make a confidence interval for the quantity mu1 minus mu2. And again, y bar 1 minus y bar 2 plus or minus t star Okay, so I'm going to pause the video right here and you guys go ahead and work through this. Yes, do a 95% confidence interval, sorry. Let's see how we did. Alright, so just gonna take our values here, and so in the center of our interval we put y bar 1 minus y bar 2, so 69.5 minus 64.5. So based on our sample, we see a difference of 5 inches between the two sample means. And then we do plus or minus. Okay, so let's look up our critical value. So we have to figure out our degrees of freedom. So we're going to have 20 plus 15 minus 2, which gives me 33 degrees of freedom. So we go to our t-table and we look for 33 degrees of freedom, and we see, okay, we don't have 33 degrees of freedom, but we do have 30 or 40. So we always round down, so we're going to go to 30 degrees of freedom, 95% confidence, so the number I use is 2.042. Okay, so we use t star equal to 2.042. Okay, and s1 squared over the root of n1 plus s2 squared over the root of n2. So this is just plugging in the numbers that we have. So I've got 3.1 over 20, 3.1 squared over 20 plus 2.8 squared over 15. Okay, so I'm going to just punch all this in. 3.1 squared over 20 plus 2.8 squared over 15. I'm going to take the square root of that, and that gives me that, and then I multiply it by 2.042. So I got 2.045. So 5 plus or minus 2.045, pretty much we can, it's like 2 inches, right? But if we want to be super precise, we can, okay? So essentially, it goes from 3 to 7 inches, our confidence interval for mu1 minus mu2, or, you know, with more precision, 7.045 and 2.955 to, right, I think, yeah, 2.955. Okay, so what is the statement that I'm going to make? So before I would say something like, I'm 95% confident that the mean this is between such and such. What am I saying here?
The overlap is between that,
It's not the overlap.
or that they're similar.
So we are making a statement about mu1 minus mu2, okay? So there's a few ways we can phrase this, but one way is I can say I am 95% confident that the mean height of men, or the height of the average male, mean height of men is between 3 inches and 7 inches taller, or 7 inches higher than the mean height of women.
Could you do it the other way around as well?
Mm-hmm, we could. Okay, so in this case, I say it this way because I've got mu1 minus mu2, and I'll explain it. But so we are making a statement about the difference between mean heights, or we're making a statement about how mu1 compares to mu2. So in this case, we're saying I'm 95% confident that the mean height of men is between 3 inches and 7 inches higher than the mean height of women. Okay. And so going back to our original question, is the average height of an adult male different from the average height of an adult female? What is our answer? Our answer is yes. And how does this tell us that the answer is yes? Because it's
There
not.
is a difference.
Because it's not 0, right? Our confidence interval says that 0 is not a plausible value, right? 0 is outside of our confidence interval. So that gives us evidence that they are indeed different. Okay, so our confidence interval does not contain 0. So it provides evidence that mu1 and mu2 are different. Okay. Let's see. All right. What if, so here when I labeled these things, I arbitrarily called this one sample 1 and I called this one sample 2. I called the men sample 1 and the women sample 2. I could have also, just as equally valid, I could have labeled the women sample 1 and the men sample 2. Okay? How would that have affected the work or the confidence interval? Yeah, so so everything, all the data is the same here, right? I mean, technically, I mean, these would switch places, but this quantity would still be 2.045, right? After all is said and done here. The only difference would be here I'd have 64.5 minus 69.5. Okay, and so if I had switched them around, I would end up getting, you know, -5 plus or minus 2.045. Okay, and then my confidence interval would go from -7 to -3 or something like that. Okay, so essentially it's going to be exactly the same, and the only difference here is if I want to go strictly off of the confidence interval in our interpretation, I would say something like, I am 95% confident that the mean height of women is between 3 inches and 7 inches lower than the mean height of men. Okay, so we're saying the exact same thing. In one case I'm saying men are taller than women, and in the other situation I'm saying women are shorter than men. Those are equivalent statements, and you're going to be saying the same thing. The signs might change, and you might go from positive to negative or whatever, but whether you say A is larger than B or B is smaller than A, you're saying the same thing. Okay. All right, so in this situation, our confidence interval does not contain 0, so it provides evidence that they are different. On the other hand, if, you know, let's say I made a, you know, let's say we make a confidence interval for mu1 minus mu2, okay, and we do, let's say we took like SAT math scores or something like that. Well, there actually might be a difference between men and women in SAT math scores. I don't know why. Maybe the verbal side, there's not as much of, it's not a very clear difference. Okay, so if you take a small sample, you might get something like, so let's say you had, let's say sample 1, again, we'll say men, and sample 2, women. Okay, so we're looking at SAT verbal scores. And so let's say your confidence interval, 95% confidence interval, ends up being, so we're going to just pretend like we did the math, and so your 95% confidence interval ends up going -50 to +30. Okay. So now we say, you know, I am 95% confident that the average SAT verbal score of males is between 50 points lower and 30 points higher than the average SAT verbal score of females. Okay. And
Doesn't really like tell you anything, though.
it doesn't. You're right. This is much less exciting. Or I don't know if exciting is the right word, but it is not able to answer our question. If the original question was, do boys and girls have different average SAT verbal scores? How can I phrase this? Is the average verbal score for boys different from the average verbal score for girls? That might be the question that we have. Let me write that up there. Okay. Is the average verbal SAT for boys different from the average verbal SAT for girls. Okay, so our confidence interval ends up being -50 to +30. Okay, so what is our answer to this original question?
Would we say that there's like, it's like yes and no because it includes 0, but
Yeah, so
there's also evidence that there's a difference.
okay, so yeah, so we might be tempted to say, is the average verbal SAT for boys different from the average verbal SAT for girls? We might be tempted to say no, okay? But we shouldn't say no, okay? So in this case, 0 is in our confidence interval, okay? Or is within the confidence interval, okay? 0 is between -50 and +30. Okay. So this means we do not have evidence to say yes. Okay? But we cannot say no. All right? And I know it feels weird saying that, but you know, we do not have evidence to say the average verbal SATs are different. Okay, but we cannot say that they are the same. Okay, and in fact, anytime you take a sample, you will never actually be able to say that the average verbal SAT scores are the same. Even if your samples end up being exactly the same, that doesn't tell you that the populations have the same average or same mean. Because the only way you can find out if the populations have the same mean is to get the actual means of the populations, which means you have to observe the entire population, which we're assuming we can't do in statistics. Okay.
The 68% this is only 95, 60, well, 68%.
So that 68% comes from the empirical rule saying 68% of the time things will be within one standard deviation of the mean. So if we're dealing with sampling distributions, our y bar will be within one standard error of mu 68% of the time.
Can we use the p-values at all?
So p-values will come next when we cover hypothesis tests, which we'll do immediately after the midterm. So okay. So is this all right? So this is what we can say, but you cannot say that they are the same, okay? Because this requires, to say this requires that we know mu1 and mu2, which requires measuring the population. Okay, so so when you do statistics, a lot of times you end up making statements like this. We don't have evidence to say they're different. Does that mean they're the same? No. And that's just the nature of a lot of things, It's a lot of times get these slightly unexciting conclusions. But those not exciting conclusions are just as important as the exciting ones, okay? Although, you know, there's like a publication bias against unexciting conclusions, but it's, we should not look down upon those, okay? If you just say, you know, we looked at 1,000 people and we found no evidence of a difference, you say we found no evidence of a difference, you know? But it's very difficult to say, to make any kind of definitive conclusions. So, you know, there was the vaccines and autism controversy, right? Because there was a medical journal article published that that said there's a link, which was later retracted, and then you know, a lot of studies were done, and the only conclusion you can make from a study is we found no evidence of a link. You know, can you prove conclusively that there is no link? And because of the nature of this thing, you always have to say, no, we cannot prove conclusively that there is no link, but based on our study, we found no evidence of a link. And, you know, there have been lots of studies that say the same thing, but there's no way physically to say conclusively we have proof that there's no link. So.
Every statistics is everywhere. Everything you read,
Mm-hmm.
everything.
Yeah. So yeah, we're doing yeah. So with inference, this is kind of where we end up going. Okay. So that wraps up confidence intervals for a difference between means. Are there any questions on all of this stuff? Okay. Okay, we'll take a short break, and then we'll do a little bit of review for the midterm.